This video will cover the first of two Latin rectangle extension theorems. Okay, so let's let L be a Latin rectangle with P rows. P rows, Q columns, and entries from a set of n, say, with the size of this set of entries is going to be equal to n. Okay. And it's kind of straightforward to see that P and Q have to be less than or equal to n. You know, you've got each row is supposed to have distinct entries taken from the set capital N, so the length of the row has to be less than or equal to n. And similarly, each column has distinct entries taken from the set capital N, so the length of the columns is less than or equal to n. So both P and Q have to be less than or equal to n. Okay, and so now we're going to suppose that Q is equal to n, i.e. L has maximum possible height, so maximum possible width, but we're going to assume that that P is less than n, so it doesn't have the maximum possible height. It doesn't have the maximum possible number of rows. Okay, so the claim is that we can add another row to get a Latin rectangle of shape P plus 1 by n. Okay. And if we can do that once, then of course we can just do it again, right? We can just apply the same result once more. And so we just keep on adding more and more rows until we've got a Latin square. Shape n by n. But so yeah, the kind of core of the proof is just to add one row, and then you can just do it again if you need to. So this is the first of two Latin rectangle extension theorems. This is the easier one. Okay, and so how are we going to do this? How are we going to prove it? We're going to prove it as an application again of Hall's marriage theorem. We're going to use a particular version, an application of Hall's marriage theorem that we mentioned previously. Let's just recall how that goes. So we had this proposition. So suppose we have a matching problem. Sets A and B and column sets Cj. So Cj is a subset of A for J and B, and corresponding row sets Rk contained in B for K and A. Okay. And remember, as we've discussed previously, if you know the row sets, you can find out the column sets and vice versa. You could just draw it as like a rook diagram if you wanted. Okay, so so suppose we've got a situation like this. And suppose we have a d, some constant d greater than 0, with the column sets all have size at least d, and all the row sets have size at most D. Okay, so then then the claim is that the problem is solvable. Okay, so I won't kind of go through the proof of this again. We had the proof earlier, but just as a quick reminder of how it goes, we can write down a certain set X, count the size of X in two different ways, and by counting the size of the same set in two different ways, we end up checking the plausibility condition for this, that the size of, if you have a subset U of B, then the size of the candidate set CU is greater than or equal to the size of U by this counting argument. And once you know that, you can apply Hall's marriage theorem to see that a solution exists. So we're going to use this proposition in order to prove the Latin square extension thing. Okay, so here's kind of the Latin square that we're looking at. Or Latin rectangle, right? So the columns are labelled 1 up to n, like so, and the rows are 1 up to p. Okay, and now we're supposed to be adding a new row. Okay, we're going to take B to be just this set 1 up to n, and A is n is whatever set we're taking the values going in the table from. That might just be the set 1 up to n, or it might be some other set of size n. Okay, and then Cj is going to be okay, so we've got our J here, and then we're looking what can we put in this box. Okay, okay, and so what can we put here? Well, things that we're allowed to put there, with the Latin square property, we're not allowed to have any repetitions in any column. So we're not allowed to have any of the stuff that appears above this box. Okay, and okay, and so of course you've got P boxes here. Okay, and so there's P different things, and they all have to be different, right? Because we're assuming that the original L is a Latin square, a Latin rectangle, has the proper Latin property, so there's no repetitions in this column already. So you've actually got precisely P different entries above this box, and those are the ones that are excluded. So there's n minus P things that we can put in. Okay, so that's our Cj. Okay, so then what's the corresponding Rk? Okay, so that's a set of columns in which k is allowed to appear in the new row. So which columns is k allowed to appear in? Well, in which so that's a set of columns in which k doesn't already appear, sort of above the, in the previous thing, in the original L. So Q, this is the total number of columns, Q, minus, so I'm calling it Q, but we're assuming that Q is equal to N, but I'll just write Q here to sort of emphasize that we're thinking of it as being the number of columns. Okay, so this is okay, so that's Q minus the number of columns that already contain K. Okay, so how many of those are there? But K appears once in each row. Therefore, P times. Okay, so what? Each row, the rows are size n, and they've got to have. So you've got to have n different entries taken from the set capital N. So that means that that's capital N has size n, so you've got to have each entry exactly once in each row. So this K appears once in each row. So altogether it appears P times in different columns. Right, it's not allowed to appear more, because it's a Latin rectangle already, it can't appear more than once in the same column, so these are P different columns. So we're seeing that the size of RK is going to be Q minus P, which is N minus P, because Q equals N by assumption. We said we were looking at a Latin rectangle of maximum possible width, so Q is equal to N. So that means the proposition is applicable with D equal to N minus P. Right. So remember that we had this proposition we wrote up a minute ago. That was about a situation in which in all the column sets CJ had size at least D, and all the row sets RK had size at most D. In fact, in this case, it's kind of even more regular. The column sets of CJ all have size exactly D, and the row sets all have size exactly D as well. But anyway, that's good enough. So that means there exists a solution. So there's a solution for this matching problem. Okay, so what does it mean to say that this matching problem is solvable? So what does it mean to solve a matching problem? It means that for each of these candidate sets CJ, you choose a particular element. In this kind of job allocation situation, that's CJ is going to be the person who's being given job J, and so you've got to and these elements, all they all have to be distinct, right? I mean, in the kind of job allocation situation, that's the condition that you don't give more than one job to the same person. Okay, so we've got these distinct elements, C1 up to Cn, lying in the set Cj. So we can take so the condition Cj in Cj means we can add Cj at the bottom of column J. Without creating a clash. Remember, capital Cj, that was a set of things that we're allowed to place in that box. In the new row in column J, it was the set. Was the set, the full set capital N, but we removed all the things appearing above that box, which would create a clash. So this one's allowed to go there. Okay, so we can add, and then the second condition. So that means we can add the list C1 up to Cn as a new row. Okay, so that gives us a new row of our Latin rectangle. And because these guys are all distinct, we don't create any repetitions in the new row. And because of the CJ and CJ condition, we don't create any repetitions in any column. So once we've added this row, we've still got a Latin rectangle. And remember, we said, so here we were assuming we had a Latin rectangle of width n and height p. Now we've extended it to height p plus 1. But we can just keep on doing it and carry on doing it until we've got height n, which makes it a Latin square. Okay, so we'll do an example to illustrate that last theorem. So let's look at this Latin square here. We'll do 1, 2, 4, 5, 3, and then 5, 1, 2, 3, 4. Okay, so that's a Latin rectangle. That's our L, okay, and we want to extend it to make a Latin square. Okay, so first thing we have to do is to work out all the candidates for going in the next row. Okay, so here, so actually it's just right over here. So we've got n is q is 5. So the set of possible entries is 1 up to 5, and then we've got 5 columns. And here our original P is 2 because we've got 2 rows. And so the set of possible candidates here, okay, well, let's write it over here. So if we do in column 1, okay, what are we allowed? We're not allowed 1 or 5 because they've been used already. So we have 2, 3, 4 as the candidates for this column here. And then candidates for the next column, you're not allowed 1 or 2, they've been used already. We've got 3, 4, 5, and the third column, we've got 4 and 2 used already, so we have to have 1, 3, or 5 there. And then here you've got 3 and 5 used, so 1, 2, 4, and C5, we've got 3 and 4 used, so 1, 2, 5. So as we mentioned in the proof of the proposition, we're always seeing that these all have the same set size 3, which is our this was n minus p. Okay, the number d that appeared in the proof was n minus p, and in the current case that's equal to 3. All these sets have size 3. Okay, so we need to choose elements from these various sets, and they all have to be distinct. So we could just don't have a terribly systematic way of doing this, but I mean the theorem tells us it's possible to choose distinct elements, one from each of these sets, but it doesn't really tell us how to do it. Well, let's just try. Okay, so we try. We'll might as well put the 2 here. Okay, and then we've got to choose one of these guys. Well, let's just make it the 3. Then we've got to choose one of these. Well, we can't choose the 3 because that's been used already, but we could choose the 1, so apparently. So let's just try the 1. And then here, we've got to do 1, 2, or 4. We can't do 1 or 2. They've been used already, so we've got to have a 4 here. And then here, we've got to have a 1, 2, or a 5, and the 1 and the 2 we've done already, so we have to put a 5 here. Okay, so so now we've added a new row to this Latin rectangle. Okay, okay, so we've added one row, and as we say, you can just do the same thing again, so now our candidate sets have changed. Okay, the candidate sets shrunk in each case. Candidate set here, we used the 2 there, so we've just got 3, 4. We used the 3, so we've just got 4, 5. We've used the 1, so we've just got 3, 5. We've used the 4, so we've just got 1, 2. And then here we used the 5, so we've just got 1, 2 again. Okay, so now let's try to fill in the next row. Okay, so well, let's try just putting a 3 here. It's not guaranteed to work, but yeah, I mean, it's guaranteed that there is a solution. It's not, but you might have to search around for it. You might have to backtrack and things. But we'll try just putting a 3 there. Okay, but we put a 3 there. In the column 3, right? We've either got to have either a 3 or 5, but we've already used the 3, so we've got to put a 5 there in the middle column. Okay, and now if we look at column 2, right? We've got to have a 4 or a 5. We can't have a 5. We've already got a 5, so it's got to be a 4. Okay, and then here we, in column 4, I've got to have a 1 or a 2, and apparently it does could do it either way apparently. So we'll just try putting the 1 there, and then but then once we put the 1 there, we have to put the 2 there. Okay, so that looks good. We've added a 4th row, and now we have to add a 5th row. In fact, we don't have any choice about how to add the 5th row. We have to add the we've got to there's only kind of one candidate in each case. We've got to put in the one thing that's missing for each column. So we don't have a 4 in this column yet, so we've got to put the 4 there. We don't have a 5 in this column, so we've got to put the 5 there. We don't have a 3, so we've got to have a 3 there. We don't have a 2, have to put that 2 there. We don't have a 1, so we've got to put a 1 there. Okay, so now we've got a Latin square, a 5 by 5 Latin square, so that's an illustration of the theorem that we proved at the beginning of this video.